Hello everyone, welcome back. So continuing from where we stopped, we shall be talking about neural networks again, and I want to start with why do we need neural networks. So we've understood the history of how neural networks came to be about and the process that they've gone through up to this day. So now we want to understand why do we need neural networks. So if you remember what we talked about, the perceptron, the perceptron is sort of like the grandfather to neural networks, and one of the major issues with the perceptron is that it could not separate data that was not linearly separable, and the main thing with neural networks is that they can help us distinguish data that is not linearly separable. So for example, if you see these two graphs, you can see data that on the left is sort of two curves, and of course there's no single straight line that can separate this, but neural networks are able to learn how to separate this sort of information. And on the right, you can also see where it's circles intertwined within each other, which is the blue circle within the red circle of data. And so obviously there's no single line that can separate between these two different classes. And so neural networks, on the other hand, are able to learn how to separate these two classes. And this is because there's a theorem called the universal approximation theorem, which is that a multilayer perceptron, which in this case is a neural network, can model any given function. So any neural network, even with just a single hidden layer, in theory is able to model any given network. So we could decide to use logistic regression with multiple polynomial features, but you'd require many polynomial features, which could be in the hundreds or even thousands of features, and of course that will affect training time and may not be very tractable. So if we look at a single neuron, it looks very similar to what a perceptron looks like and what we've seen before. So here we have a neuron with the inputs being x1, x2, and x3, and then at the end it produces an output which we would call h of x, and the subscript is theta because theta is the output is based on the weights, and theta over in terms of the weights. So between the inputs and the output, we see an activation function there. So the activation function is what decides what the output will look like, I would say. So most activation functions are used to help neural networks be able to handle nonlinear data. So many of them are nonlinear in nature, and we can see examples of them like there's a sigmoid, which you must have seen from logistic regression before, and this is basically converts any value between any value on any integer into a value between 0 and 1, and then you have a tanh, which will convert any value into a value between -1 and 1. And then there's the Rayleigh function, which basically, if values are less than 0, those are converted to 0. And if a value is above x, x being positive, then the value it will return is the value of x itself. So as you can see, these help these networks develop a nonlinearity and allows them to work with data that is not linearly separable. So going back to our single neuron, so if we understand that x1, x2, and x3 are the inputs, and then weights, which could be theta 1, theta 2, all the way to theta 2, or at times described in terms of w, so it could be w0, w1, w2, and w3 could be applied to this, and then at the activation function, this then decides what the output is going to be. So this is in a way similar to what we had with the perceptron, but the difference is that this now has a nonlinear activation function. And so what we receive on also as the output is not limited to being a 0 or 1, and could basically be anything. So this is now an example of a neural network, and as you can see, this is a blown up version of what the single neuron was. So here we have multiple neurons, and so if we look at layer 1, in this case being the input x1, x2 to x3, and then layer 2 of the neural network, which is often called the hidden layer, a1, a2 to a3, and then layer 3, which is the output and normally combines the data from the hidden layer. So what we have as layer 2 as the hidden layers could be multiple layers. It may not only be one. So particularly when you're looking at deep learning, you'll have hidden layers that go from 3 to 4 to 5 to 6, depending on what is required. So in this network, it's called a fully connected neural network because each output is connected to the output. Each input is connected to the output in the next layer. So as you can see, X1 is connected to A1, A2, and A3, and X2 is connected as well to A1, A2, and A3. But in other versions of neural networks, this may not be the case. So data flows from, inputs flow from X1, X2, X3, which are the inputs, and then these are then moved to A1, A2, and A3 with different weights, and then the values are then moved all the way to layer 3, and then an output is produced. So the forward movement of data from the input all the way to output is called the forward propagation. And so what you'll see at the top here are sort of functions that show what the different layers are going to look like. The different neurons in different layers are going to look like. So from X1, let's say, X1 will send its output to A1, A2, and A3. And then X2 will also do the same and send its output to A1, A2, and A3. And so when the value that A1 is going to receive is going to be a combination of the weight on X0, X1, X2, and X3. And X0 is often added as a bias term, and you may not see it in this diagram, but X0 is a bias term. And by bias, it means that we basically don't train on that term. And so it doesn't have, when we're doing back propagation, for example, we don't really adjust the weights on the bias term. So A1 is going to be the combination of data from X0, X1, X2, and X3, each multiplied by the weights, which you see as theta. So theta 10 means the weight on X0 from layer 1, and theta 11 means the weight on X1 from layer 1, and theta 12 is the weight on the input X2 from layer 1 as well, and that goes on that way. So once we sum the values from all the different inputs X0 all the way to X3, we then put this into a function G, where G in this case could be the activation function, which could be the sigmoid or the ReLU or the tan H that we've seen before. And so this then gives it the nonlinearity. And so each of these weights, combination of weight and inputs together with the nonlinearity is passed on to layer 2. And then when we're looking at now from layer 2 to moving on to layer 3, which is the output, we then do the same thing. So we have weights for A0, A2, A3, and we also have weights for each of them from theta 10, theta 11, theta 12, theta 13, and each of these is multiplied and multiplied against the input to get a summation that is then taken through the sigmoid function. So the sigmoid function then returns the output, which we see as h theta x. So this is a forward propagation, and so for each of the inputs, in terms of batches, it goes through this forward propagation and produce h theta x. So how does the model learn? So how the model learns is what we talked about was what brought neural networks back, and is the most interesting thing about them is the backpropagation algorithm. So just like in most machine learning algorithms, we're trying to minimize the cost function. In this case, we can call it j theta. And where theta are the weights in the network. So the weights in the network determine what j theta is going to look like. So we need to find the weights that correspond to the minimum of j theta. And that's what the backpropagation algorithm helps us with. So the backpropagation algorithm is a way to calculate the derivative of the cost function, but through iterations and with ease, and using a bit of gradient descent. So how it works is that first you'll have a forward pass like we saw before with the forward propagation through the network all the way up to the output, and then when we get to the output, we shall then have to calculate the difference between the actual value, because neural networks are supervised machine learning algorithms, so we're going to have the actual output, and then this together with the value that is returned for each output from the neuron. So once we get the difference, we then propagate this error back to the network that was, back to the neurons that gave it to us. So for example, if we look at the neural network shown here, if we have h theta and then we have our actual value as y, so the difference between h theta and y is the error, and so what we do is we propagate this error all the way back to a1, a2 and a3, and then at a1, a2 and a3 we then propagate this error all the way back to adjust the weights between x1 and the different neurons in layer 2. So what this allows us to do is sort of, in a way, it approximates the gradient without us having to actually calculate the gradient of a very large cost function for j theta. This is used in combination with gradient descent, which allows us to continuously update the network and eventually get to a point where we have a trained model that approximates what exactly we're trying to model it against. So implementations of neural networks in Python are multiple, but the most common ones you're going to find are scikit-learn, which is one if you're developing very simple networks, TensorFlow, which is a package from Google, and PyTorch, which is another implementation that is backed by Facebook. So next we'll be trying to see how we can implement an actual neural network in practice. Thank you.